one very classic question that shows, it's a nice example of how Pythagorean theorem is used. You often will see these questions about a baseball diamond. And that's because a baseball diamond is in the shape of a square. That actually tells me a lot because, and we saw an example of this on our last lesson, but a square, one of the key features of a square is that it has 4 congruent sides. So we'll get to that in a second, but also it has to have all 4 right angles. So I can draw one right there. I know that all 4 of those are going to be right angles. This is going to be key to understanding if we're doing Pythagorean theorem stuff. The main idea here is, can you find a right triangle? If you can find a right triangle anywhere in the picture, then you can use a squared plus b squared equals c squared. And take that a step back, you can only find a right triangle if you can find a right angle. So I definitely know a square has right angles in it. That's one of its key features. The distance between each of the consecutive bases is 90 feet. So that is telling me the distance between, if you start and you hit the ball and you run from home plate to first base, you're going to run a straight line distance of 90 feet. Well, the fact that this is a square means that all of these are 90 feet all the way around, 90 feet around. So those are 2 key components of a square. Let's look what the question is actually asking us for. It says, what is the distance from home plate to second base? Now, that's not how you run on a baseball field. You run from base to base, but it's asking you, if this is the setup of a baseball field, a baseball diamond, then what is this distance right here? So we're going to draw that in there to illustrate. This is what the question wants to know. And then, oh my goodness, look what we have. We have a right triangle. This is honestly just asking you to find the length of the diagonal in the square, which you've done a couple questions like that. But this is a realistic example of what you would be calculating when you did that. So this means that 90 and 90 are the legs of the right triangle, because they are the sides, if we're still not quite getting this, they are the sides that create the right angle. And that means this distance that we're supposed to find from home plate to second base is the hypotenuse. That is C. I can tell that because it is directly opposite the right angle. So if I can find a right triangle in there anywhere, then I can use Pythagorean theorem to solve for missing pieces. I can use a squared plus b squared equals c squared. In this picture, once again, a squared is 90, b squared, 90 squared plus 90 squared. Both of the legs are 90 because this is a square. And I'm looking for this hypotenuse, the distance from home plate to second base. 90 squared plus 90 squared. I type all that in my calculator at once, because as we talked about before, your calculator will do, please excuse my dear Aunt Sally, and I get 160, well, 16,200 is what I get, equals c squared. Again, we of course know that that would be the square attached to this hypotenuse if there was one drawn there, which there's not, because we now know the algebra behind it and we don't need to draw the squares to know that we square things. But we do absolutely need to remember this final step. If you're trying to get back to a side length, you have to square root both sides. So I square root 16,200, and this tells me the distance from home plate to second base is approximately 127.28 feet. I rounded that to the nearest hundredth, as we've been practicing, and you can type in your calculator and check how I rounded that and make sure you're clear on all your rounding. Okay, so this one had started a picture, but we still had to draw in what it was we were actually trying to find. And I'll say this a few times throughout, but the key is, can you find a right angle? And if you can find a right angle, can you turn it into a right triangle? Because if there is a right triangle there, then you can use Pythagorean theorem. Okay, question number 2, there is no picture there. So let's read it together and let's see, can you find a right angle? And if you can find a right angle, can you find a right triangle? So this one says you have a 15-foot ladder. You can picture a ladder. You want to place it so that the ladder reaches to the top of a 12-foot wall. So imagine a ladder leaning up against a wall. The question is, how far from the base of the wall do you need to place the ladder? Let's talk about a ladder and a wall. Is there a right angle in this? Well, yes, the right angle is not going to exist with the ladder, but the right angle is going to exist with the ground. So if I just start, I'm going to draw a line that just represents, this is the ground. I'm going to assume it's fairly horizontal, and I'm going to assume that the wall built next to it is probably vertical, or it's supposed to be. And if I have that set up there, then yes, I do have a right angle. with the ground and with the wall. Now, what else is involved in this story? A ladder is. And what do you do with the ladder? Well, you lean it up against the wall. So the ladder is actually now the hypotenuse because it is opposite the right angle. So I was able to find a right angle. I was able to create a right triangle in this scenario. Now let's just label the things that we know. My dog is doing a lot of ear flapping right now. So it's a 15-foot ladder. So the ladder is 15 feet. That's the ladder part. That means I know the hypotenuse. I know the hypotenuse is 15. I also know that I'm trying to reach to the top of a 12-foot wall. Okay, so I know one of the legs, I know the hypotenuse, and I am looking for the distance. How far from the base of the wall do you need to place the ladder? I'm looking for this other leg. There we go. I have a right triangle, so I'm ready to use a squared plus b squared equals c squared. I know c this time. I am missing one of the legs. So with that in mind, I'm ready to set this up. A squared plus b squared equals c squared. This time I do need an inverse operation because the variable, anytime, and hopefully you've started to notice this, anytime you're missing the hypotenuse, you can just evaluate this part, square them and add them together. Anytime you're missing one of the legs and you know the hypotenuse, this is when you're going to have to subtract one of the smaller squares from the hypotenuse squared. And again, you can just type that part right in your calculator, 15 squared minus 12 squared, and you will find the other square. You will find that that middle square is 81. Hey, that's a nice number that I'm very familiar with. That tells me when I square root both of these, I'm not going to have to worry about a decimal approximation. This tells me that I should place the ladder 9 feet away from the base of the wall. Which realistically, if I did that, I don't know if the ladder would stay up. I don't know. You guys can go outside and test it out if you want. But this, according to this, if I want it to fit exactly at the top of the 12-foot wall, then I need to place the base of my ladder 9 feet away from the base of the wall. Okay, so that one we had to create our own drawing. But again, the key is, and the next couple we're going to create our own drawings too. The key is there a right angle in this story? And if there's a right angle, is there a right triangle? So number 3 says this. This would be a very important question for Jill. Jill's front door is 42 inches wide and 84 inches tall. She purchased a circular table. Okay, the table's a circle. That's not going to have a right triangle in it. But she knows the circular table is 96 inches in diameter. That means that the table, remember, diameter of a circle is all the way across. So that's the widest distance across the circle. Any circular object, its widest distance is the diameter. So here's the really important question for Jill. Jill wants to know, will the table fit through the front door? That's what Jill wants to know. That's an important question for Jill because how's she going to get it in her house if it doesn't fit? So I know the circular table doesn't have a right angle in it, but the door does. If she has a rectangular doorway, which is standard for most of us, a rectangle, so you can just draw a rectangle here. A rectangle definitely has a right angle in it. So I'll draw a right angle in one of the corners. I know it's in all of the corners, so it doesn't matter which one. Here's what I know about her front door. It's 42 inches wide and 84 inches tall, which 84 inches is 7 feet. She purchased the circular table that's 96 inches in diameter. Now, I know clearly the table will not fit straight up and down because that's less than 96. It won't fit across because that's way less than 96. So my only hope is if it fits, if I twist the table diagonally, will it fit there? So what I need to know, guess what I just drew? I just drew the hypotenuse of a right triangle. The diagonal of a square or a rectangle can always become the hypotenuse of these two right triangles. So I'm going to use Pythagorean theorem to calculate the diagonal of her doorway because that's my only hope. Let's see if that's big enough. I know the two legs, so I go 42 squared plus 84 squared equals x squared. That's the diagonal of my doorway. I'm going to type those in my calculator and let my calculator do the squaring and the adding for me. But because I know both the legs, I am just adding them together. That is 8,820. And now, of course, to get the actual length, that's the squared length, I need to do the inverse. That happens to be more than I would like on this. I need to do the inverse and square root both sides. Okay, square root of 8,820 is not a perfect square, but in these real life scenarios, oftentimes the decimal helps us more than the exact form. 93.91 inches. So, is that table going to fit through her door? No, the table won't fit. Because that's the only place that it could possibly be big enough. If it's not tall enough, if it's not wide enough, then the diagonal is your only hope. And that means Jill's got to figure something else out. Maybe she has like a sliding glass door, some French doors in the back of her house that will open up wider that she can get it in. Otherwise, maybe she should have calculated that before she purchased the table. Okay, let's look at one more example here where we're going to draw the picture. This is talking to me about a soccer field that is a rectangle. So guess what? I'm going to draw a rectangle. This time it's a soccer field. And the coach is asking players to run from one corner to the opposite corner. So guess what? That is, again, the diagonal. My pen went a little crazy. I'm just going to leave it there. It's fine. So this rectangle here, it tells me the soccer field is a rectangle that is 100 meters wide. And you could think of that as the height and this one the width. I'm just going with scale-wise what makes sense. 100 meters wide and 130 meters long. Okay, so once again, and I drew that here and I drew that here, but no, on a rectangle, it could go anywhere. That could be 130. It has to be really. And because it's a rectangle, there's a right angle here. There's also a right angle here. There's right angles everywhere. So once again, really what I'm asking you for is the diagonal of this rectangle. So as we look at this mathematics here, here's what we're saying. We're saying this is a leg, so 100 squared, plus the other leg squared, 130 squared, is equal to the hypotenuse squared. Let your calculator do this evaluating for you. You know both of the legs, so just type in your calculator 100 squared plus 130 squared, and then square root both of those sides. And sometimes I do that all at once if I have a calculator that I understand how it works. Look, I can type in 100 squared plus 130 squared, and I get this number, 26,900, and then I can immediately go second square root, second answer. And I've got that right there. Hit enter, and there we are. It says 164.01, so I'm going to say that this is approximately, the coach is going to ask them to run, they're going to end up running about 164 meters if they have to run the diagonal. And that will be the longest single distance, but please notice it would actually be longer if they ran both of the legs. So if they had to, if you had one player that was running from this corner down there, they would actually go farther doing both of those legs than if somebody ran across the diagonal, which should make sense to you if you thought about that in real life. If you're trying to do a shortcut, you'd run across the diagonal. It is the longest side by itself, but it's shorter than the two legs added together. Okay, one last question to show you how we use Pythagorean theorem. And I do see some right angles in this picture, and I see some different things. Let's read this and see what this is about. A plot of land, so that's the green part in my picture, has a creek running diagonally through it, as shown in the figure. So here they've got this blue creek drawn in here. This green stuff is a rectangular plot of land. I can tell it's a rectangle because it has 4 right angles in it, and I have this creek running diagonally through it. They have all these measurements laid out on this plot of land. So somebody's gone through and measured all these lengths here, but they haven't actually measured the creek. So if I was just looking at this map and I didn't want to go out and have to actually physically measure the creek, could I use this little plot of land here? Could I use this little map to figure out the length of the creek? And at this point, if you want to pause and try it out first, you can and come back, or you can just watch me do it. I see some right angles, but I do hope that you notice here that this actually has 4 sides. That is not a right triangle. And even if you were trying to think of it as one, what would be the legs and what would be, that's too many measurements, right? Because it's one too many sides. That's a quadrilateral. So what if instead I kind of create my own little right triangle in here? I know if I draw this line here, and I'll do my best to make it straight, but it probably won't be. If I draw a straight line across there that's parallel to that one, I know that this measurement is also 66 because it's parallel to that piece going across, as long as I make it perpendicular over here. So there's my right angle, and there's my right triangle. That would make the creek the hypotenuse. But I can only do this if I can figure out that leg. So how do I go about figuring out that leg? Well, I can just do some basic subtraction here. Look at this piece here, from there to there. That tells me it's 72.1. So I'm going to do 72.1 minus, look at this piece over here. If I take that 72.1 and I subtract out this distance on the land, that will give me this leftover distance over here. So I'm going to do 72.1 minus 43.3, and that gives me 28.8, which is also my missing leg measurement. Now I found a right triangle, I found the legs of that right triangle, and I'm now ready to calculate the hypotenuse, or the length of the creek. So here I go. I'm going to go a squared, 28.8 squared, plus b squared, that was 66 squared, the other leg, equals, and I will call it c, not only for hypotenuse, but c for creek right now. But it is the hypotenuse, so make sure it's the biggest one over here by itself. Type in your calculator 28.8 squared plus 66 squared, and that will give you this value, 5,185.44. That is how big the hypotenuse squared is. So of course our final step here is square root both sides. And again, if I've already typed all of that in my calculator, I've got this number sitting there, then I can just go second square root, second answer, depending on what kind of calculator you're dealing with. If you're on like an iPhone calculator, that decimal's just sitting there and all you have to do is push square root and it gives it to you. So, and it gets me right about, it's not exactly this, but it is about 72 meters long. That is the length of the creek. There are many, many applications to Pythagorean theorem. And in fact, when you combine Pythagorean theorem with what you call right triangle trigonometry, which is something you'll learn a lot about in 10th grade, as soon as you put those two concepts together, Pythagorean theorem and right triangle trigonometry, that's where almost all of our modern construction skills become possible, is with those pieces of mathematics.